I request all the participants to mute the mic, and also we can off the videos so that we can save the bandwidth and the speaker will be able to present the topic. So on behalf of IEEE Kochi subsection and IEEE students branch of SEMS School of Engineering and Technology, it is my pleasure to invite all the participants to this talk by Dr. Ali Alfred on the introduction to cyber physical systems, and to enlighten you more on the IEEE activities and about the talk, I invite the chair of Kochi subsection, Professor Santosh Kumar, to the meeting.
Yeah, thank you, Dr. Varun. So indeed, we are very happy to have a very distinguished guest today, Ali Alfred. Welcome to Cochin, and I think it is evening time to you, right?
Right.
Yeah.
It's okay. 7 p.m.
Yeah. So IEEE Kochi subsection is very vibrant IEEE activities. IEEE Kerala section in particular is the world's largest section in terms of membership, and we grab many awards from IEEE headquarters every year. Last year, the prestigious MGA Outstanding Large Section Award was given to our Kerala section, and a lot of volunteers help to build up and propagate the theme of advancing technology for humanity. So we are very happy to have you here, sir. So today, Alrisa Jalafe will be talking about a very important topic, cyber physical systems and the security aspects. As you know, our globe is actually connected to the cyber world. So we were connected in terms of internet, but nowadays every device is getting smart, and everybody is now virtually connected, right? So there are a lot of advantages while we are connecting to the virtual world. So this physical and the cyber world is connected. A lot of advantages are there, but still there are a lot of challenges, and in terms of security, a lot of things we have to be very careful. I think our professor today will be enlightening us on these kind of issues and how we can deal with all these things. So most welcome, Alrisa Jolfe, to this presentation, and we are very happy to have you here. So to formally introduce you and welcome other guests who are attending this talk, I request Dr. Varun Menon to formally introduce the speaker and welcome the audience. Thank you, Varun.
Thank you, sir. It is my pleasure and my privilege to introduce my very good friend, Dr. Ali Alfred. So Ali Alfred is leading the Masters of Information Technology in Cybersecurity in the Department of Computing at Macquarie University, Australia. Prior to this, he worked as a lecturer at Networking and Cybersecurity at Federation University, Australia, and also at the Temple University, Philadelphia, USA. His research is mainly focused around cybersecurity, IoT security, human-in-the-loop CPS security, cryptography, AI and machine learning for cybersecurity. He completed his PhD in applied cryptography at the Griffith University, Australia, and his PhD topic was on an exploratory topic about the confidentiality problem of 3D content in mixed realities. So it's indeed a very good and very exciting topic of PhD research. And he received the prestigious IEEE Australian Council Award for the paper published in the IEEE Transactions on Information Forensics and Security. And he has been awarded the grant by IEEE Signal Processing Society for presenting the same conference, same paper at the International Workshops on Information Forensics and Security in Rome. He is a senior member of IEEE and ACM Distinguished Speaker and he is a guest editor of many top transactions and journals like IEEE Internet of Things journals, Internet of Things Journal. And it is our pleasure and our privilege to welcome such a very leading speaker in cybersecurity to this venue. And in spite of all the busy schedule, he has agreed for this talk. So on behalf of Kochi subsection and SCMS School of Engineering Technology Students Branch, I would like to express my sincere thanks. And we wanted to have you in person here for the talk. Probably maybe after COVID, we will have an opportunity to invite you in person and discuss more on research opportunities along with the IEEE section here. So thanks a lot. And I also welcome all the participants to this talk, and over to Dr. Ali Alfred Jolfai.
I would like to thank Varun and Dr. Kumar for having me here today, and thank you very much for your hospitality. I would be really glad to be there with you in India, and I hope that the COVID situation, hopefully, fingers crossed, gets resolved very soon. So all of the border restrictions will be lifted so people can travel all around the world. And thank you very much for the kind introduction. So for today's talk, as the event is organized by the student branch, I thought that perhaps I could talk about a very broad aspect of cybersecurity in the cyber-physical systems. So I assume that for the today talk, my audience are mainly students. So before I start the talk, I want to introduce myself. I know that Varun has explained about my background and what I'm doing right now. As you know, I'm actually working at Macquarie University, and I'm leading the cybersecurity program here for the Department of Computing at Macquarie. Macquarie University is one of the biggest university in New South Wales, Australia, on the eastern side of Australia. And Macquarie is located on the northwest of Sydney in a beautiful area which is called Ryde. And this picture is actually the location of where the Department of Computing and my office is. And as a part of my job, I usually teach units around applied cryptography, digital forensic investigation, which could potentially help for in digital investigation of crimes, and offensive security, that deals with how you can hack into the systems, networks, web applications, etc. And as Varun explained, I got my PhD in applied cryptography, and I mainly I'm interested in security of control systems. So anything that deals with control, like cyber physical systems, like Internet of Things, that we need to control the operation of that system. I'm interested into that specific type of research. So as Varun already explained, I jumped from this slide. And right now at Macquarie, we are actually developing a smart city lab where we can demonstrate various types of cybersecurity issues with respect to critical infrastructure, such as transportation system, power system, water system, gas pipeline, and etc. And we are in the process of actually working with the Department of Defense here in Australia, so we can get our cybersecurity labs security cleared, so that we can take project with respect to defense. And it also provides a good opportunity for prospective students, especially from India, from your section. And you are more than welcome that if you decide to study in Australia, you can later on contact with me and I guide you through the application process. If indeed you want to visit Australia and you want to study a cybersecurity program at Macquarie University. So let us go to the main topic of talk that is about the security of cyber-physical systems. So to explain what CPS or cyber-physical system is, imagine a beautiful day like today. It's a Saturday here, and perhaps you wake up in the morning and you try to make breakfast. So what you may use is you may use gas that might come from gas pipeline, or you might use electricity to turn on your stove, or you might need to use you might need to make tea. So how do you make tea? You might need to use electricity for your kettle to warm up the water, or you might use gas. Later on, you might need to take shower, right? I mean, when you wake up, you need to brush your teeth, take shower perhaps, and you use water system. Now you're coming to this seminar, you're using your laptop, you're using internet. Before this talk, maybe you wanted to check your banking information online. You might have had a light lunch. So if you look at all these things that, is on a day-to-day basis, everything is really interconnected. We cannot imagine living or starting a day without having a clean water, without having electricity. You need to have energy to turn on your laptop, to keep your houses cool, warm. You need to have a proper agriculture system to provide food for every houses. So you can maintain your living. You need to have a proper transportation system. And all of these systems are kind of interconnected. We cannot imagine one without another. For example, we have water energy nexus. One of the ways that we can generate energy is from water. We have lots of hydro plants that could potentially help us to generate electricity. Or transportation, now we are moving towards electric cars. Vehicles that you use on transportation, they use electricity to power up. So everything is getting more connected. And actually this phenomenon of, connectivity of things actually has a long history. I mean, if you look back through the history, that everything was mechanical, and gradually we had this industrial revolution. Everything, we were capable of producing things in mass, and then we have all this control technology to be able to produce automation. We had robotic factories, and after a while, something that people call it IoT 4 or Industry 4, that now we have Internet of Things and all this networking architecture to help us, let's say, to maintain the operation of a meat production line, for example, or maintain the operation of a production line in the factory using these advanced technology. And if you look a little bit closer to these systems, I mean, as a whole, I mean, into cyber-physical system, you see that they have a specific characteristics. Usually, we have a number of systems that the output of one system is input to another. It's like a serial of different systems, or they can be in parallel. One of the examples that I explain is water energy nexus, that the input to the power generation could be water system, or when we have electric vehicle that connects to power grid to charge, it basically gets electricity from another system, which is electricity. Or if you look at your building management system, it involves various components. I mean, we have a system that controls your blinds, for example, to control the level of light. You have a system for controlling the temperature. You have, a system to check, for example, if there is any hazard in the building, a smoke detector, and etc. and etc. And all of these systems are working together. So if one part of the system doesn't operate well, it might influence the operation of the other parts. And so that's one thing that is really important. And when we talk about this, cyber physical systems, one of the things that is not really well understood at the moment is the hidden interdependencies between these subsystems, as well as the hidden interdependencies between the communication network and the physical system itself. Just to give you an example, bushfire in Australia is a very common thing. Last couple of years, actually, when there was a big bushfire, I think it was in 2019, if I'm not mistaken, and fire actually reached to Sydney, very close to Sydney, and many buildings actually were set on fire. And some of the buildings here, they have building management systems. So when there is a hazard or excessive heat outside, they automatically lock, the door, everything gets locked. And because of the excessive heat of the fire outside the building, the air conditioning system start working more, and this basically sucks all the smoke from outside the building into the inside of the building, and has made many people to pass out. A similar incident happened in Washington, in the US, where there was a wagon that got stuck inside the tunnel, mainly because the air turbine inside the tunnel was set on fire. So the control system basically stopped the train in the middle of the tunnel. And because of the excessive heat, again, this train, its air conditioning system started working much faster. And many people actually were passed out because of this excessive smoke. So this is something that that is not really correctly studied, and most of the time that's something that is missing, that can create a lot of problems, a lot of cascading failures, and that's something that that is observed as a result of the fact that we have many systems that might have interoperability issues. I mean, you might know very well about communication network, and you might know very well about the mechanical aspect of a control system. But when you want to control a number of systems that work together, you need to know what is the impact of your communication protocol on the physical operations, which may put your people, your users, at risk, at potential harm. I mean, another example I can give you is the game Pokemon Go. I mean, it was very popular quite a number of years ago, that people were playing and trying to get points, and they had to kill Pokemon, in different parts of the city. Sometimes it takes them to the edge of a cliff, middle of a highway, and put them in safety and risky situations. So many similar problems that are actually not really observed, mainly because most of the systems that we have right now are mechanical. Gradually, when we have in IoT and more connectivity, and we're talking about AI, everything is getting more advanced and getting connected to internet. And these vulnerabilities that were not observed in the past, they appear. So these things, many of them existed quite many years ago. For example, when we talk about power network, that's a technology that was created 50, 60, I don't know, many years ago. And the main aim was producing electricity to turn on the lights in every single house. Nobody thought about security. Who cared? You cared about producing energy, reliable energy with the least amount of cost. But nowadays, to improve your operation, because you don't have enough people to send all different parts of your power network to observe and to check the data and what's happening, if there is any fault in the power line. So you try to use sensors to capture this information, and that's where the problem appears, because when these sensors want to interconnect and send the information, that's where that people can wiretap the signal and try to hear, what's happening there, and they might be intrigued to inject some bad information to create loss, cascading failure, or any type of intent. So as I explained, any cyber physical system, in my opinion, I mean, everyone has a different opinion. I mean, I look at it through this graph. So I look at it through a cloud, fog, edge, and IoT layer. That at the left-hand side, at the lowest layer, we have the sensors or IoT that basically captures the information through the environment. For example, if you look at the transportation system, every single car has sensor. It has brake fluid sensor. It has, for example, camera to detect, the cars in front. It has proximity sensor. If your car has adaptive control, cruise control, it uses that sensor to adjust the distance between your car and the car front. So a lot of sensors in a car. So, and we have, a central processing unit inside the car that basically captures this data in order to do some sort of analysis or data analytics in order to maintain the operation of the vehicle. And at the upper layer, when you look at the road, so you usually see or roads are packed with cars, and cars usually drive in groups. So for example, if you see, it's I don't know, it's maybe human behavior. When you see you are behind a group of cars, you try to speed up to catch them, and you just drive in a group of cars. So roads are, are contained with a lot of group of cars, and these groups that they basically are driving on roads together, they usually get information from roadside unit. So at the moment, we don't have, this standard on our roads. So our cars are not that much smart enough. Maybe few cars are like Tesla, or in future it might come out that can subscribe to a computer on the side of the road. But you can imagine, as an example, I can tell you this roadside unit could be traffic sign. So you just adjust your speed with respect to your traffic sign. So it tells you 60 kilometers, 80 kilometers. Imagine this is a digital traffic sign that controls the speed with respect to the flow of the traffic. So all these groups of cars basically are subscribed to a roadside unit. And at the upper level, we have zones that we have a groups of these groups, or let's say a neighborhood of a city that basically is controlled by a computer, let's say in a local traffic management center. And if you go up and up, maybe then Kerala, and then you have India as a whole. So you can see the flow of the data and how much big data we have when we talk about the whole India. But when we go to the single car, we have much less information that we are dealing with. And this category, this way of classification actually shows us when we are talking about the sensor level, we are dealing with a very low latency operation. For example, when you see a hazard on the road, for example, imagine a person jumps on the road in front of your car. You need to immediately slam on the brake, otherwise you're going to hit him. So this decision needs to be made very quickly. So if this decision is not made fast, it can create hazard. Or when you talk about groups of vehicles, when you see somebody change lane, you try to adjust. You don't, change your lane if your opposite lane is already filled in with another car. But you don't need to make decision as quick as, slamming on the brake when you see somebody jump on the road. So as you go up, the latency requirements decrease. So you can, when you are inside the traffic management system of India, you don't need to make decision in a second. Maybe, you can decide about the general routing of the cars about an hour. I don't know what the policy is there, but you don't need to make decision that much quick. But when you are in the sensor layer, you need to make your decision much faster. This is an overall architecture that shows how the dependencies actually work in a CPS, or let's say cloud fog edge computing architecture. And usually in cyber physical system, we have we are dealing with control systems. By control, I mean a feedback control loop like this, that, for example, I spoke about traffic management system. So the controller here is the traffic management center that basically wants to manage the routing of the cars in order to reduce the traffic jam. So for this aim, the traffic management system needs to have a number of sensors, which are cameras, which are situated on different locations of the city, or they might get information from, police officers across the city. And based on that sensed information from the operation of the cars, and your traffic management system make a decision that, what is the best decision to make in order to reduce the traffic flow. And basically, in order to apply those commands, it has some actuator. You need to, for instance, reduce the speed at some part of the city in order to reduce the traffic jam, increase the speed at another part. So such a system, such a feedback control loop, in order to send message, for example, from cameras to your traffic management system, we need to have a network that helps you to deliver the data from one point to another. So if you look at this system, every single part of this system could potentially be hacked or could potentially be perturbed. And any perturbation in any part of this system could have, may have bad outcome, which we will discuss about it further. So now that we know, how the cyber physical system works and what CPS is, a question that crosses your mind, why cybersecurity is an issue. So as I mentioned, many of our cyber physical systems, they were initially developed for the reliability aspect rather than security. And when the Ethernet protocol appeared, actually all the problems come from the Ethernet protocol, that the devices try to communicate with another using a common language, which we call it Ethernet. All these problems appeared because it increased the surface for attack. And that's where the problem appeared. So what is the aim of an adversary or a malicious person who wants to create a cyber attack? What is the aim here? What is the aim of the bad guy here? So if you want to understand the aim of a hacker, the first thing is to understand what a security property is. So when we speak about security, we usually, refer to, some known features like confidentiality, integrity, availability, and et cetera, and et cetera. So all of these characteristics could potentially be perturbed. And any perturbation in any of these characteristics could help the bad guy or hacker to reach their goal. So if you look at it in a broader perspective, this is the concept map of cyber physical system. And as you see, the landscape is very broad. When we talk about cyber physical system, we are dealing with control systems, we are dealing with scalability issues, we are dealing with validation and verification, we're dealing with cyber issues like intrusion detection, privacy, confidentiality, resilience to APT, and etc. The landscape is very broad. And specifically, when we talk about cyber attacks, So if you look at any control system or a cyber physical system, as I explained, it has various components. We have a sensing component that sends the data from the environment. We have communication that sends this sense information from sensor to the computing component, right? And then computing component using a communication network sends the data to an actuator to actuate a command. And we have a feedback control loop here. You know, for example, in your building management system, you have some sensors in your room. When the temperature drops, you know, the controller sends command to your air conditioning system to, you know, to increase heat. So we have a sensing and actuation, and then we have a feedback loop that we can sense again and send the command to the controller to see if our actuation worked or not. So all of these aspects could be hacked. You know, when we talk about communication, you know, hacking in there could be a type of a civil attack, could be corruption of the data, could be software malfunction, many other aspects. So when we talk about actuation, you know, what problems can we make in actuation? You know, for example, you can turn off the power, so your actuator doesn't work without power, right? You can tamper the hardware of your actuator. You can do various things. Or when we talk about feedback control loop, you can perturb the integrity of your feedback control loop. You can you know, inject some bad data. So the data that is going back to the computing component is not the correct data. When you talk about computing hack, you know, you can have some kind of worms in your system. You can have viruses, Trojans. You can corrupt the data. You can change the software inside your computing component and all these various aspects. So you can see the landscape is very broad. And in order to understand, to better understand what security is, you need to know about the hacker's mindset. So speaking of a hacking mindset, this is the overall procedure that a hacker usually tries to you know, identify vulnerabilities and then try to make exploits. So in the first stage, when you have a system, the first thing that you do, you try to do a reconnaissance. You know, you want to see if there is any vulnerability. For example, if you see a network, you try to probe if there is any open port to attack. So you do a network scanning. So once you did your network scanning and identify the open ports, you know, you try to do something that's called Google dorking. You know, you try to find out, for example, if you have an open port, how you can obtain access to that specific port. You know, you search for Google. Google is your friend. So once you found the way that, you know, you can get into that open port, you can, you know, send some commands and try to find out, for example, what is the operating system. Try to get some kind of errors. When you get the error message, you cross-reference this error message with a database that is called CVSS, Common Vulnerability Scoring System, and CVE, Common Vulnerability Exposure, that tells you what type of vulnerability exists in a specific operating system with a specific version. For example, if I know the version of the Linux version that is, you know, that your controller works based upon, I know that what type of vulnerability exists, so it can help me to make an exploit into the system. And that's the case for most of the cyber physical system. For example, when you talk about you know, water treatment plant, how often do they update the software of the controller that controls the slice gate of a dam, for example, or controls the filtration process? I would say it's not very frequent. So, you know, if you see your mobile phone, you just make it updated. You know, if you look at iOS, it usually updates things every week because they want to patch. But when we talk about a very broad cyber physical system, normally this is not done at that much frequent level, and they are quite, imposed with lot of surface for attack. So once the hacker gain access, what they do, they try to maintain their access. They try to, um, delete the log files and make the track clear. So this process is a very simple process actually. And to give you an example, I mean, I think about maybe about 8 years ago, if I'm not mistaken, FBI actually found that a group of hackers, they basically infiltrated into a control system of a dam in Rye Brook that is about 100 kilometers on the western side of New York. And those group of people who hacked into dam, they had the access to the control of the slice gate for more than 2 years. And more than 2 years, nobody knew that somebody was in there. And they found about the attack when they published the outcome. So they had produced some report of how they actually controlled this mechanical operation, and that was a trigger that they found that somebody is actually meddling with the critical infrastructure. And those group of people were actually students. So they were bachelor, master students. So I just wanted to say that the complexity, when we talk about complexity of attack, usually we're talking about low-hanging fruit, and we have many of such low-hanging fruits when we talk about critical infrastructure specifically. Now, another example is a recent attack of colonial attack to oil rig in an oil distribution in the US that they use a malware and they forced the company to pay the ransomware, and they paid it. So such a thing could happen everywhere. It can happen in Australia, can happen in India, can happen in China, everywhere. And nowadays we are facing a very a strong level of attack that is called advanced persistent threat. So such type of threats are not naive, are not accidental. They are people who are like insiders who already work in the utility company. They know how the operations work, what systems are in place, what protocols are in place. So they know about everything. And they can remain in your system for a long period of time in a coordinated way without being detected. So nowadays we are dealing with such type of attacks, and we need to find out ways, such as, game theory techniques, could be one potential solution to predict the next move of such type of adversaries to mitigate any type of perturbation that they want to cause to the system. So as I explained, we have various type of vulnerability that very normally when you try to search your vulnerability, you just do search what is the error on the software, what is the error message, when you ping a server, what is the error message that you get. All this information can help you find out how you can gain access. There are lots of zero-day vulnerabilities in every system, and they are missed, and that's the reason why every day we see a new type of attack, because they were not well understood in advance of the system being developed. We have lots of misconfigurations. For example, when we talk about transportation might get its sensors from different companies. There might be some tender. You might have, at the moment it might be Cisco, then it can be Microsoft, many other companies, or even, SMEs could come into play, and they can add on various sensors that they might not work with the same protocol as, other type of sensors. And this can create misconfiguration. So misconfigurations, it could be a main cause of cascading failure. I brought two examples in the beginning of my talk when the air conditioning system tried to suck smoke out of the building. And that's a very common problem that happens everywhere, because programmers are usually not system, administrators. They are not aware of this type of misconfiguration, and that's something that should be assessed by a cybersecurity team to provide a pre-supply chain assurance to the company before taking those items or equipment into operation. This is a list of various type of vulnerabilities that could potentially exist in many of our systems, web applications. For example, it could be a SQL injection flow, cross-site scripting. There could be various types of broken authentications, cross-site request forgery, etc. and etc. So that you can basically do a fuzzing, identify all the types of vulnerabilities that you can potentially find and try to make an exploit. So to be more specific, now let us talk a little bit more about three different areas of cyber-physical system. So that cybersecurity could be a major issue. The first area is a smart grid. So a couple of years ago, when I was actually at Temple University, I was working on a grant which was funded by National Science Foundation in USA, which was about the cybersecurity of the smart grid across the Pennsylvania state. And it was a collaborative work between Temple University and Missouri State University. And we tried to actually work on some of these interdependencies that potentially exist between the communication network and the power system. So if you look at the power system as a whole, this is a general architecture that we have there, that the power is generated from, it could be hydro plant, it could be a solar plant, nuclear plant, etc. And then it's being sent to some transmission substation. We're talking about very high voltage electricity that it's being sent across the country, right? So we have very high voltage electricity, and it's being sent to another sub transmission and substation, which we call it distribution substations. And the role of distribution substation is to break down the power into a smaller voltages to be fed into the industries, houses, different parts of your country. And this network is quite large. I mean, if you just Google and see, I'm sure that you can find out the information about the electricity distribution in Kerala, because usually, at least in Australia, I know this is public information, that if you Google, you can find out. You can see this network is quite large. And when we talk about power, it's a very critical operation that if you have fault, you need to act very quickly, because if, imagine there is electricity fault in a transmission substation, if you don't turn on or turn off a relay very quickly, you might end up burning a very expensive, I don't know, $500,000 transformator. So you need to be very careful and act vigilantly. And we're talking about very high voltage electricity, right? It's not something that I just take some probe with my hand, I will get electrified. I mean, if I just want to check what is the current voltage in a specific part of the electricity network. So to make our work much easier, we have lots of sensing devices. For example, some of them are remote terminal units or phaser measurement units, which are more advanced, that basically have isolation to the high electricity, and they can capture the data from this high voltage lane in a high frequency, Nyquist frequency, and they send this information to a phaser data concatenator that basically aggregate this information and make them like a train of data and send this information to a control center. So in every substation, for example, we have a control unit and a control room that basically monitors the operation of the power. For example, how much voltage is coming in, how much power is being distributed, is there any fault, everything is protected. So if any change happens in the power load, it can quickly change the topology, or it can quickly aim to feed the power with respect to demand. And we have various types of operation that a local control center might do. One of them is a state estimation, because you want to know what is the current usage and what is the demand, so you can adjust that energy with respect to your demand. For example, nowadays in Australia, we have many houses that we have solar panel. So when, for example, the demand goes up, the control unit might use this electricity from the other houses to feed it into network, or they might borrow the energy from somewhere else to provide this high demand of electricity in a high power consumption time zones. So we have a state estimation process. We have contingency analysis. We have system stability monitoring. For example, if the frequency of the AC power changes, we need to make it stabilized. We have optimal power analysis and etc. So we have a wide range of operations. Some of these operations, they require a very fast decision making, and those are especially for protection. So for example, if there is as I mentioned, there is electric fault, you need to make an action to turn on and turn off a relay in less than 4 milliseconds. And some of the others, we don't have that much latency. For example, usually a state estimation could happen in a scale of minutes or hours. We don't need to make it in a scale of seconds or milliseconds. So these are two types of operations that we actually have within a smart grid. So this is the type of protocols that we actually use within a smart grid. We have two types of protocol, as I mentioned. Everything that we have in internet, we have in a smart grid as well. But speaking of the power protection and the protection of the relays, not only just in the power system, any kind of SCADA network, we use a protocol that is called GOOSE, generic object oriented, I think single event, if I'm not mistaken, and a sampled value protocol. So these two protocols usually are based upon 3 layers of networking. So usually, when we talk about networking, we have 5 layers. We have physical, data link, network, transport, and application layer. But because time is very critical in here, the way that engineers, many years ago, they tried to solve the problem of the latency requirement, they just try to delete some of these networking layers. So what they did, they said Goose protocol only uses Ethernet layer and application layer. There is no network layer because we have a single hop communication. The phasor measurement unit get the data from the high voltage lane, and we send it to PDC, phasor data concatenated. So it's a single hop communication, and we basically don't need any IP or networking layer in here. So it only operates based on 3 layers of networking just to save the time. So we are able to make our decision within 4 milliseconds if anything goes wrong. So we can quickly protect the relays in terms of an accident or a fault that can occur in the system. And if you look at the common standards and protocols, they actually even allow the sending of the messages in plain text, because most of the practitioners know that there are already many devices in the field that they basically use the very old microcontrollers that they are not capable of running crypto operations. Because when we talk about crypto operations, that could happen in many of the processors. It takes a lot of time. When we have a very old microcontroller, it might not be feasible to maintain the 4 millisecond time requirement. And that's something that we try to address the problem by proposing a new mechanism that is based upon a permutation-only encryption. And we try to address the security of it using a key management system. So basically, it's permutation-only scheme is not a secure method. But and the reason for that is that if you have a number of pairs of ciphertext, by a simple comparison, it has a period of comparison that we can calculate. That's usually an order of a logarithm term in here. And to solve this problem, we calculated this upper bound that we are allowed to use the same key. And using this upper bound, we tried to sort the key with a new counter value that is being generated by our key management protocol. So the amount of information that is available to an adversary or a hacker to basically make any meaningful deduction from the keys, it becomes almost very negligible. And we did various types of security analysis with respect to well-known attacks, and we've shown that the chances of an adversary obtaining any information is very low. And also the other advantage of the protocol was that it can maintain it was the only algorithm that could maintain the latency requirement of 4 milliseconds. So that was an example of the type of problem that exists in the state estimation process and in the protection applications in the smart grid. Another type of problem is a state estimation that, as I mentioned, a state estimation is a very old and naive numerical method that existed many years ago. I mean, we have a method called Newton-Raphson. I mean, it's many centuries old method that basically here we have a large system of equations, right? So for example, imagine you have a big power system and you have a large number of equations that each equation represent KVL, KCL. So if any of you have done electrical engineering, you understand what I mean. So you have a large system of KVL, KCL equations, and you want to find out what is a snapshot of this system. I mean, what is the solution to this system? 100 equation, 100 variables. So that's a technique in numerical method, Newton-Raphson, that basically has a sanity check that takes some input, and after a number of iterations, they try to find out what is the solution for this system of equation. So here for the power system, we need to know what is the current voltage. So with respect to that, we try to manage the power flow. But this process could potentially be hacked. I mean, if you imagine that many of these sensors could, be hacked, or if the communication network between these sensors and the local control center get hacked. So adversaries potentially being able to inject bad information. And if this bad information being received by the state estimator, it can potentially make a wrong decision. And this wrong decision can create a cascading failure, can create electricity blackout. And that was the topic of research that I actually, myself and a group of researchers at Temple University, we worked on that. And we actually shown that the state estimation process could be bypassed. And we've shown the attack bound So with what perturbation bound, we can basically, or let's say what type of bad data or bad vector could potentially bypass the threshold detection or bad data detection of a state estimator, and after how many iterations we can fool the state estimator to make a wrong decision. So just this is an example of, I mean, what we did. I mean, we just did some simulation on a number of system. This is one of them on an IEEE 14 bus, which is a very simple system that we actually tried to show that after a number of bad data injection, let's say after 10 rounds, we can fool the system that the current voltage and current of the system is something else. The same as here. And we also, so the aim of this attack was actually for showing that after a number of iterations, you can fool the state estimator that the range of, or let's say the snapshot of the system is something else. And if this solution is above 5%, positive minus 5%, bound, then that's something that's called hazardous. So as long as this changes to the voltage and current is within 5%, it's acceptable. But if it's beyond this 5%, that's something that could potentially cause problem. So that was the other type of problem that we actually investigated. So another type of example for CPS is the intelligent transportation system. So if you look at the history of a transportation system, you can see, it has changed quite significantly. I mean, if you look at the history, 120 years ago, this is a picture of the 42nd Street in New York, and this picture is for a few years ago, before COVID. So you see quite a number of change happened in the area. And nowadays we have lots of digital equipment. We have cameras, we have a speed signage, we have digital enforcement technology like tolls. We have cameras that can detect if you're wearing a seatbelt or not. Various type of technologies that they use various communications, such as vehicle-to-vehicle communication, vehicle-to-infrastructure, or vehicle-to-controller, in order to maintain the operation of traffic on the roads. And if you look at this system, a little bit more deeply, we see that it also follows an edge computing architecture, that we have a number of roadside units that they capture data from the cars on the road. And this data could potentially be used to inform police, for example, how to track individual car. It could be used to control the traffic routing. It could be used to help the vehicles to know about the traffic hazard and various types of things. So if you look at it, you see it's very useful technology. And such a technology, when we talk about transportation, it actually has quite a large number of problems that, for example, some of the problems are as follows, that the first problem is multi-tenancy. So when we talk about transportation, we might be, the transportation system might be working with different companies that all of them have, different architecture, different protocols, different requirements, and each of them have different hardware, different software, different vendors, and this can create, misconfiguration, and handling these could create a problem by itself. And we have lots of security problems, privacy problems, access control issues. For example, how can you maintain the security of data being transmitted from the vehicles to the roadside unit? Encryption could be a solution to this, but when you have, let's say, a traffic scenario that there are many vehicles on the road that they need to communicate with each other, for example. And when they have to communicate with many vehicles at the same time, basically the processing unit of the car should be capable enough to basically encrypt and decrypt the information within a short period of time that meets this time latency and also meet the safety requirement. For example, if there is a traffic hazard on the road, your car needs to make a decision or a slam on the brake in less than 20 milliseconds. So if this security mechanism create a delay for your decision making, that your 20 millisecond time latency requirement is not met, it can create a hazard or a safety problem. But these are the type of thing that we potentially see or for the future technology, because at the moment, when we talk about transportation, such as standards are at the concept level, we haven't been able to see them widely, but maybe in next few years, we might see our roads, maybe 30%, 50% of the road will be fully autonomous vehicle. So we are not far from that moment. And that's something that we really need to care about. And as I mentioned, encryption could be a problem, because when we talk about most of the encryption protocols at the moment, the operation of these encryption protocols could be very complex and time consuming, which might not meet the time latency requirement that is required for the safety application in transportation. Another type of problem is privacy. For example, when you drive on the road, you have to use the traffic management system. For example, you need to follow the road rules. So you need to be subscribed to it. So one of the information that the traffic management system collects from you is your location, from where to where you go to. So having this location, even if it is anonymized, could potentially leak your identity. For example, you might every morning, you might go from your home to your work, right? So if your work is, for example, a school X or company X, and if they know from where you actually started your move and where you stop, it's very easy to detect who you are, because how many people, for example, working in that specific company live in that neighborhood, live in that city. People are coming from different locations. So even though your data is anonymized, still this pattern could leak information. Or when you drive, this correlation of information could leak more information, more data that could perturb your privacy. But these are the type of problem that we potentially deal when we talk about transportation system. So this is one of the security approaches that could potentially be used in the future transportation system to sort out the problem of the complexity of encryption and to some extent the privacy problem that could happen when you share your information with the roadside unit. Because our assumption here is that you don't trust the transportation network, but you have to use it because you want to use the road. So when you subscribe to the roadside unit, it basically takes your information. It takes your data from where you go to where. For example, you want to search information on internet, you have to use Google. Even if you don't trust Google, you search your words through Google. So you need to protect yourself. So the idea here is, one potential solution to protect yourself while you're driving in a road infrastructure is, as follows, that you could potentially use a grouping technique. So, for example, if you imagine vehicles are driving together on the road as a group, so they can nominate a group leader, and they send the information to the group leader, and group leader basically permutes the information. So, your location could be, dislocated to location of another car. So the group leader send this perturb, or let's say permuted bit stream to the roadside unit. So when roadside unit gets this data, of course, why it wants this data? Because it wants to know how many cars are driving on the road, for example. What is their speed? But when these entries in a matrix are dislocated, so the values of cars are dislocated between each other. So the roadside unit doesn't exactly know what information belongs to which car. So it kind of protects the identity of the people because the data is dislocated. And the only person who knows, what is the correct combination of these values is the group leader. So it's without having the consent from the end user, which is the driver, a police enforcement agency will not be able to identify which location belong to which person. So that's a kind of solution that could potentially happen. So for the permutation, one of the methods that you can use, you might use various random number generators that has good characteristic, and it has a high period, so it won't be detected easily. And we picked one of these random number generator, and we've done a couple of tests, randomness tests, to see what is the output. Is it random enough to be used for the transportation application? We used a very famous test that is called NIST SP 822. That's a combination of a number of, I think, 15 tests that basically checks all the values of, or let's say the patterns within your beta stream. And we weren't able to identify any pattern. So which showed that the characteristic of our key stream statistically is good. It doesn't disclose any information. And we did some sort of analysis to find out the upper bound that we need to change this permutation key, which is similar to the process that we use for a smart grid application, using a key management system. And using this perturbation bound, we were able to show the success probability of an adversary to finding any meaningful information from this obtained data is very negligible. And we ran this on various types of ARM controller. So this is an example that we run on Cortex-0 48 megahertz ARM. And we were able to show that the speed requirement meets this 20 millisecond safety requirement. And such a method is quite advantageous because it allows you to still be able to use the full capability of your hardware. And also, you don't need decryption. So it's a kind of, there is a terminology that we call it searchable encryption. So it's not a kind of encryption. You have all your data, but basically this data is dislocated within your matrix. And you still have the exact values, and you're able to know, for example, what are the speed, what are the location, but you don't know where it belongs to. So that was an idea that we had in mind. So Varun, how much time I have?
Yeah, you can go ahead, sir.
About 10 minutes.
Yeah.
Okay. So another type of application is the industrial control system. So this is an example of an industrial control system that we have a plant. We have a sensor that captures information from the plant, and we have a controller that gets this data from sensor, and then this controller need to actuate. This is the feedback control loop. And when the controller actuates a command, we have a digital to analog component or zero order hold that basically tries to impose or try to force your plant to maintain its operation. When we talk about plant, it can be a rotor in your cooling system. It can be, for example, a rotor for your car. It can be, let's say, a control system of an elevator that wants to adjust the level of the elevator with respect to the ground. It could be adaptive cruise control in your car. So we have control systems everywhere. And usually such systems, they have, a state space model. So it's a very simplified here. And we have a transfer function that maps the input to output. And the aim of your control system is basically to converge the output of your physical operation into a specific certain value. So for example, when we talk about, I just brought an example of an elevator. When you get on an elevator, you want, ideally you want your elevator to pause or stop at the same level of the floor. And you want to converge it, the error to zero, the error between this floor distance to zero. That's what the controller does with PID, we call it PID controller, proportional, integral, and differentiator. And it tries to adjust and balance it. And speaking of cyber attacks, when you look at this problem, attacks to control system could be that, it could be a resonance, or it could be an oscillation. If you create an oscillation inside your, in the output of your control system, it can potentially create harm. Over the time, if you just, if you have a rotor and you just inject bad data, high voltage, like a they call it like a triggering, like some shots, and then you can create some damage. And sometimes, when you do this oscillation, by the end of this oscillation, you might have the opportunity to create some steady state error, right? And that's what the aim of the control system is, to reduce this error to zero. But as a hacker, you want to optimize it in a way to increase the error. So you do an opposite word. So, whole world is trying to make it optimized in order to reduce error, but you want to increase the error. So this is the hacking mindset, right? So hackers' aim is to increase this error. And we can formulate the hacker as, as a different, when we talk about control system and this transition model. So hacker is, if you observe it mathematically, is like a new component added to your system. So this hack could be happening different parts. It can be inside your, on the right-hand side after your sensing component. It could be before your digital to analog system. It could be inside your control, everywhere, right? So this is just an example. And sometimes the overshoot, that was an oscillatory attack. This is this is a different type of attack. You want to create an overshoot, transient overshoot. So, you just want to make a temporary shot. And every temporary shot could create, it can place extra effort for your control system, use up more energy to maintain the balance. And sometimes if this shot of, bad data is very large, your control system is not able to basically, contain it. So if it's above the, the threshold, the tolerance of the system, it wouldn't be able to control. And you see, after a while, this transient overshoot becomes very oscillatory. And so So one of the works that we actually did, I mean, without going much into detail of it, was with respect to such type of adversarial attacks, that we know that we have an advanced persistent threat in the system. So when I say advanced persistent, it means I know somebody is there, but I don't know from where. So we know that somebody is trying to perturb the input to a control system, and we see oscillatory behavior, and controller tries to mitigate it, right? So controller, when it sees this perturbed data, it tries to actuate with respect to that information that it has. And of course, because of that wrong information, it creates wrong actuation, right? The result of your PID controller is not correct. So you don't see a desired output that you expect. And that's where that you can, with respect to this pattern of behavior, you can understand something is wrong. So when we talk about, if the hacker does an injection very large, then of course you can quickly understand, right? Because if it's too large, you understand something is wrong. So what hacker does, he does numerous times. So for example, he attack, once now, after 10 seconds, after 10 seconds, after 1 minute. So in a different order or times, tries to do some, transient movements in order to reach some steady state errors and gradually add up to it, right? So for this kind of pattern, which is very difficult to detect, and our controller is not able to detect it, we can observe this pattern using some machine learning algorithms. It could be SVM, it could be deep learning method, in order to study how this pattern should be, and if it goes beyond, so such a scenarios, when we talk about APT, the threshold of the attack is not that much to trigger the sanity check, or the amount is very small. But if you add up to this amount gradually, after few number of times, it becomes something that your system gets saturated and cannot control. And that's something that we want to detect before getting into saturation state, or before reaching to the state that your controller is not able to compensate. So such a scenarios, or opinion or suggestion was that we could have a compensator or a second line of a control system that usually is not in operation. But if something goes wrong, so we have our data analytics after the controller, which basically observes the behavior. So if this data analytic understands that something is wrong or APT is detected, this controller basically goes out of the system. So we have a new controller with a new mechanism that the adversary doesn't know about. So, initially the attack was designed with respect to the original PID controller. But once we change the control mechanism, then the attack wouldn't be able to be implemented. That was the type of idea that we had in order to mitigate such kind of, we call it silent perturbation in industrial control systems. And these are some of the examples of attack. And as you see, for example, on the left-hand side, you see a kind of attack that was contained by or controller. But on the right-hand side, we have a type of attack that hasn't been able to be contained. And the output is very, oscillating, and it implies damage to the system. An example of it could be, for example, an adaptive cruise control system. So I think many of you, if you have this newer version of Toyota, for example, there is a button on your, on your wheel that when you press on it, it keeps the distance and speed of your car with respect to the car to the front. And it's a very important control system, because if you imagine you're going up the hill, your car need to basically balance its speed with respect to its weight against the gravity with respect to the car in the front. It's a very complex operation. And in such a scenario, if somebody inject bad information into your controller gradually, such that your vehicle doesn't make the correct decision, or gradually your vehicle reached, to a distance that it cannot basically protect your safety. So basically, it's too late to slam on the brake. For example, if the car in front slam on the brake suddenly, you're going to crash. So that's the type of thing that we were trying to investigate. For example, another scenario is that, one of the possibilities is the hacker basically, hacking into your system and change this sanity check. So, you have normally, for example, some threshold. If the the output of your control system goes above or below this threshold, it would be triggered as an alarm. And one of the simple ways is to hack into the system and change these threshold values. For another possibilities is like surprise attack. So for example, when you are very close in the proximity of another vehicle, for example, the hacker can increase the speed all of a sudden. So it's very hard for the controller to basically contain this type of attack. So that we can, when you think about, from a hacking mindset perspective, everything is possible, right? So we just need to think about a scenario that could potentially perturb these communications. And this is another view, similar to what we did before, that we try to use a machine learning algorithm or neural network in order to detect the output of our controller. So if in case something is going wrong, we just try to swap our control system with a different mechanism. So the hacking mechanism does not work for the new operation, because the hacker already knows how the PIT controller works, but he doesn't know about the new basically neural network. And how does he learn about the PID controller? If you have, it's very simple. If you have the input and output of a system, after a while, you can create a model yourself. You can learn how this PID controller actually operates. You can design the mathematics of it. But once this is swapped with a different system, it's very hard for adversary to quickly adapt. So we can swap between these mechanisms, and we give harder time to adversary to basically adapt its strategy. It's something like game theory. When your opponent is making some attack, you try to adjust your defense mechanism, and you want to make a decision, what is your next move. So these are some of the examples that or experiments that we did with respect to this type of covert attacks, and we try to see if our ideas can flag this type of attacks or not. We just did various types of attack with respect to the velocity of the car, acceleration, and distance between the cars, and try to see if it can create any safety hazard or not. So that was what I wanted to talk about. This area is quite large and very interesting, and I know that when you talk about various aspects of cyber physical systems, it's a very broad area, and I just tried to demo some of the parts that I actually collaborated with my colleagues in the past few years. And initially I had the idea in my mind that for this specific talk, I could go to our department and our cybersecurity lab, and I could talk in front of a smart city, that I could showcase, it could be more beautiful if I could showcase some of these concepts that I'm talking about with real practice through my camera to your audience. But unfortunately now, because of COVID, we are in lockdown and we have to stay at home. So thank you again for being with me today. So if there is any question, I'm more than happy to answer.
Thank you, Alireza, for that insightful talk into cybersecurity. So I think there are few questions. One question is being posted by Dr. Santosh regarding the contribution of the ML and DL into the recent cybersecurity attacks. That is, how can ML and DL help to reduce the cybersecurity attack? I think at the later part of talk, Dr. Jolfe had already told about the contribution of ML and DL.
Yes.
So, and some questions coming as, what are the scopes of cybersecurity? From the students, I think that is regarding the studies as well as job regarding that. So students would like to know how much relevant is cybersecurity towards their job.
That's a very good question. So I actually have very good news for many of your audience who are students. We actually have a big problem all over the world with respect to cybersecurity talents. We don't have enough talents with respect to cybersecurity to fill in our jobs. There are, I can tell you from Australian side that we have lots of job advertisements specifically for cybersecurity, but there are not enough candidates for those jobs. So there is a huge potential. I can say it's like a talent drought in the field of cybersecurity. It's a very new area that actually exists in everywhere. I mean, when we talk about healthcare, we need cybersecurity professionals, especially during the COVID time, to maintain the security, safety of patients' data. Now many patient monitoring systems are actually in operation. Or when you talk about banking system, we need a lot of cybersecurity professionals. When you talk about critical infrastructure, wastewater system, gas pipeline, transportations, many different places. We need experts in this field. And if any of you or students who really plan to do a degree in cybersecurity, I highly encourage them to do so, because from the job market perspective, there is a huge potential for people in the domain of cybersecurity to be able to find jobs, and salary perspective as well. So if you compare, the salary of an industry professional in the field of cybersecurity, I can give you an example of Australia. The salary difference between a cybersecurity professional and an IT professional is maybe $20,000-$30,000 difference in a year. If I knew, I would have shown you some of the charts that could give some comparisons between the job market for IT professional and the cybersecurity professional. So it's a huge market. And if any of your students would like to perhaps, pursue a career in cybersecurity or study a program in cybersecurity, I'm more than happy to provide information.
So I think as long as the attackers numbers increases, there is always the opportunity. The number of jobs always increases too in cybersecurity. So it will never die down. I definitely hope that the jobs will never die down, because definitely the number of attacks will only go increasing in the coming years.
Yeah. It's not a good news, but it is what it is.
Yeah, reality
it's
is
like being a doctor. I mean, they just never wish anyone to get sick, but people get sick. They need general practitioners, they need medical doctors to heal them. Same as cybersecurity experts.
Correct. So one question from Suraj is, what would be the biggest cybersecurity threats we are facing right now? Is there something specific real time that's facing now?
The biggest threat that's, in my opinion, we are facing right now is that we are actually in a phase of digital change. So we are facing a new reality that is called a smart city. You know, cities are becoming smarter. We are using more internet technology. We are using these new gadgets everywhere in around the world, and this is really worrisome. Just to give you an example, you know, you heard about the news that in Australia, because of the COVID, people were rushed into the supermarkets and bought toilet papers. Maybe same thing would, I don't know, maybe happen in India as well. I'm not sure. I think it was globally. But imagine this happens to a bottle of water. Tomorrow somebody says that the water system is being hacked. The water that you drink from tap has poison, has too much level of chlorine. And then people rush into supermarkets. There is no bottle of water. What happens? Disaster happens. Imagine, you know, in the case of US, somebody hacked into the oil distribution system. There is no fuel to fuel your car. There is no energy. So what can you do? So if you look at, you know, all these examples that we are seeing around the world, you know, as we advance more and more, we are facing more troubles. And you know, if you look at who could imagine, you know, coronavirus coming and make the whole world in a mess, that after 2 years we are not able to travel. We are all stuck in our home. So same thing can happen, you know, to any other aspect. So we are living in a different era of time, in my opinion, that, you know, we are, you know, many things are yet to come. So we need to be prepared, and we need to have that level of education and that level of preparedness to be able to face these future challenges. You know, if I mean, my suggestion maybe to people who are the smart city leaders is to have all these tactics, policies in place to be able to, you know, prepare the cities to be able to defend if any serious issue happens in the future, same as coronavirus, for example.
So speaking about cyber physical system security, it always comes to my memory of watching the movie Die Hard. That was, let's say, 20 years back. All these things was shown in that movie, like taking the entire country down just using an cyber attack. So, so I think all the students can easily relate what is the cyber physical system security. I think most of them would have watched the movie also. So we have one more question, that is one last question. There is a concept of adversarial training in deep learning, where the adversary fools the machine by providing the deceptive input. Could we use this in the CPS?
Yeah, it can be, because when we talk about CPS, we use a lot of data analytics. So when you use data analytics, you use machine learning, AI, and the same concept of generative adversarial neural network that you mentioned. It could potentially be applied there as well. And in fact, it could potentially be used for attack as well. So when you want to, you know, when I talk about attack to a state estimation, you can use a generative neural network to produce the attack vectors every time different from previous one. And it's very difficult for the system to basically defend different types of attack that can change their behavior at every single point of time. And that's really worrisome, because as we move forward, we are dealing with a smarter people, a smarter adversaries, that they can also potentially use this technology to create a disruption.
So I definitely believe that this has given a lot of insights to the students who would be probably looking more into the CPS attacks, and probably you can, most of them can proceed with more research on this CPS. And Dr. Ali is always available for any questions. And I was also there at Macquarie University 2019, a very, very beautiful university, and with a very, very good, strong, multicultural the cybersecurity department. So whoever gets more interested into cybersecurity, please do contact Dr. Jolfei, and maybe maybe a discussion can be take forward to do masters or PhD program in cybersecurity. I would like to invite our IEEE SB event chair, Vaibhav, to present the vote of thanks to speaker and all the participants.
Hello, good evening to one and all who have gathered here. Myself, Vaibhav, event coordinator of IEEE SB, would like to extend my sincere thanks to the respected speaker of the session, Mr. Alizera Jolfei, for giving such an insightful talk to each and everyone present here. Now we have a lot of people across semesters as well as faculty in the form of faculties who have attended this session. And I believe that even though we all might find different parts of this talk useful, we all take a common takeaway in the form of knowledge from this session. And I believe that even in the future talks taken by you, sir, many of us will be participating and will be looking forward to it as well. Would also like to extend my sincere thanks to our head of department computer science, Varun sir, for acting as a main link and to provide us this wonderful opportunity so that we can have this talk, and providing all the resources as well as the platform so we could come across you, sir, and then take all the knowledge from your side. And then I would like to thank all the participants as well for taking a part from the busy schedule and then attending this event. We all know that exam times are going on, but yet you guys attended the whole session, and we are quite happy you guys were here. So once again, a very good thank you to all of you, and have a lovely evening. Thank you.
Thank you very much.
So my sincere thanks to Ali Reza for his valuable time. And I'm definitely sure the way in which Dr. Santosh was listening to the lecture, I could find how interesting was the examples given by you. So Santosh, would you like to add something?
Yes. Yeah. So in fact, when I went through the title of your talk, I was just expecting very introductory kind of things. But when I started listening to your talk, it was very informative, because you have presented at least 3 problems, and the work that you and your group might have done, and the results. I was very much excited to see the way in which you do kind of research in these type of areas. I do teach a course on modeling cyber-physical systems. I use textbooks from the Rajiv Alur. I don't know whether Rajiv Alur's basically the theoretical part we used to teach the students, and one embedded course from University of I forgot the university name. There basically we try to teach the students the digital and the physical part. Basically, how we can model the physical systems. So computer science students usually they know how to use finite state automata and how to design systems, but they don't know how to model the continuous part of the system. Only control system people or physics people used to do those things, and those aspects were there in your research very beautifully. You have explained. Thanks a lot for that. Maybe I would like to interact with you in future as well.
Sure.
Yeah. So thank you so much for your time and spending this much amount of knowledge to us and to the students. Thank you. Thanks. In terms of
thank you very much for your kind words, and thank you very much for having me here.
Yeah, so
it was a pleasure being here with you today.
Thank you. Yeah.
Thank you so much. Thank you so much to all the participants and IEEE Kochi subsection for hosting this event, and a very big thanks to the speaker who has given his thanks in the Indian style to all of us. So thank you very much, and hopefully we would see you in Cochin very soon after the pandemic. And I would definitely believe that IEEE would be taking the initiative also to invite you here and Thanks a lot. Have a great day to all the participants, and thank you.
Thanks so much.
Thank you. Bye-bye.
Bye-bye.
Thank you.